We're now moving on to Unit 3. This time, this entire unit is all about intermolecular forces. So this is going to be about how molecules are going to interact with each other, what kind of forces are between them, do they attract, do they repel, how are they starting to interact. This has a lot to do with the type of molecules they are, how electronegative they are, what's their size, where the electrons are. So when you think about it in terms of just as we were before with intramolecular forces, think about things in terms of charge, where the electrons are, and distance, so how far apart these things actually are. So when you do that, it makes this kind of a little bit more intuitive, and you'll have a better grasp on what's happening than just memorizing a list of things. So these are going to be the forces that we're going to be talking about today. Dipole-dipole forces, hydrogen bonding, and London dispersion forces. So the thing about the middle one here, hydrogen bonding, is that all it really is just a super version of dipole-dipole forces. You won't really need to remember a whole lot more with hydrogen bonding. Just remember that it's a special case of dipole-dipole that are very, very strong. So let's talk about what dipole-dipole forces actually are. So anytime you have a molecule that is polar, anytime you have a molecule where the electrons are going to hang out more on one side than the other, like in this molecule here, this oxygen is much more electronegative, so it's going to be pulling electrons more towards the oxygen. So it's going to have a slight negative charge, which means this carbon here is going to have a slight positive charge. Well, if you have a big bowl of acetone in this case, or a beaker full of acetone, let's be scientific, if that were to happen, then all of these negative charges are going to interact slightly with the positive charges on this this central carbon. This force, this attractive force, is what is going to keep these molecules from moving around more. Now, remember when we were talking about the different states of matter, solids don't really move around very much. They just vibrate. Liquids can rotate, but they can't really move translationally. And gases actually have that translational motion. So whenever you have a bit of a force between these two molecules, it's going to keep these guys together. So if this bottom one is trying to move this way, it's going to have a harder time because it's being pulled towards this top molecule. So this is going to kind of keep these molecules together, which means it's going to stay liquid. It's going to stay as a liquid longer than if it didn't have this force. So this is one reason why the boiling point of acetone is relatively high. Now, if you take a look at something that just has 3 carbon molecules but no oxygen, that is propane. If you have carbon, 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 and hydrogens all around it, I'm just going to draw little sticks instead of the full-on hydrogen. In this case, this is propane. Now, when you think about it, propane at room temperature is a gas, right? You can think back on King of the Hill, propane and propane accessories. So this is a gas, but if we just added a oxygen there, all of a sudden this is acetone, and now it's a liquid. We're going from something that's a gas, and you actually have to cool propane a fair bit for it to become a liquid. Acetone at room temp is a liquid. So that the reason why is because of this dipole-dipole interaction. This attraction between a slight negative and a slight positive charge is going to keep the molecules from having that translational motion flying around all over the place, and instead keep them at that rotational motion level, the liquid level. Okay. So that is a dipole-dipole force. If you want to take the dipole-dipole interaction and turn it up to 11, what do you need to do? Well, you need something that is very electronegative. You need the electrons to really be on this side. So think about what kind of situation do you need to be in? You need to have some atom connected to a hydrogen. The reason why it needs to be connected to a hydrogen is because hydrogens don't have any lone pairs. So there's no other electrons here. It means if these electrons move this way, there's going to be a huge positive charge around this hydrogen because there's no electrons left. So what does X have to be? X has to be very electronegative in order to suck up and pull these electrons. And if that's the case, then that means this is going to be very negative. So when it comes to dipole-dipole, let me bring it back to here. Remember about Coulomb's law. It's all having to do about charge and distance. So the charge of these positive and negatives matter, and then the distance between these guys matter. If we think about it, if we turn these charges up to 11, if we really push the electrons towards one end, and in this case, remember we have something very electronegative, oxygen, and hydrogen that doesn't have a lot of electrons to begin with. So if that's the case, you get that kind of super charge here of the negative and a very positive end over here. So now we have a it's still a slight charge. It's not a full-on charge, but it's a lot closer than other dipole moments. So here we have a very negative oxygen, and if it finds another very positive hydrogen, it's going to interact, and this interaction is going to be very, very strong, or it's going to be a lot stronger than your dipole forces. So hydrogen bonds are going to be stronger than dipole forces. I said that you needed something very electronegative, and there's a little mnemonic here that you can use to remember what elements are electronegative enough for this hydrogen bond to actually take place, and that is FON. The way I remembered it is like the Cyndi Lauper song, hydrogens just want to have fun. Fun. So remember, it's a hydrogen because it only has one electron, and then some electronegative atom, FON. If these guys are bonded together, then that means the negative charge and then the extremely positive charge of the hydrogen start becoming attracted to one another. And this is a very strong intramolecular force. And you can see it's a strong intermolecular force. I mean, we have basically two dipoles here. We have, in this case, we have water and water. It's a dipole-dipole interaction. And here, two acetones, molecules, oxygen and carbon, negative and positive attraction between the two. But let's look at the boiling points of these guys. Boiling point for water is 100 degrees Celsius. That's pretty hot. And if you look at acetone's boiling point is only 56. It's 44 degrees lower than water. That means that this interaction is going to be a lot easier to break at lower temperatures. It requires less energy, less temperature to break this interaction than this interaction does. This OH hydrogen bond, this interaction is going to be very strong, very hard to break. Usually if something has hydrogen bonds, it's going to be a very polar solvent. And I'll talk about what polar solvents are in just a little bit. I've been saying that these are hydrogen bonds, and that's a bit of a misnomer. These guys aren't actually bonds. They are They are intramolecular forces. There's no actual sharing of electrons going on. Now, the reason why we say they're hydrogen bonds and not just hydrogen intramolecular forces is because these guys are so strong that for a long time we actually thought that these bonds were true bonds, that they were sharing electrons back and forth. Or they were in the same level as ionic bonds, where they were taking electrons from one place to another. So, but that's not necessarily true. It's more like an interaction, but a very, very strong one. Okay. On the flip side of that, sometimes you will hear about ionic attraction. Ionic attraction is just describing an ionic bond where you have two ions, the chlorine and the sodium in this case. They have some sort of attractive force with one another, and you would say that this is an ionic attraction, but it definitely is a bond. Whenever you're talking about things in terms of a solvent, we'll get into solvents and solutes in more detail later on, but remember, a solvent is the thing that is doing the dissolving, in this case water, and the solute is the thing that is getting dissolved, in this case the salt here. So what happens? Why is water such amazing solvent? Well, it's because of those hydrogen bonds, those strong charges on the oxygen side and the two charges on each hydrogen. So this can get in here and interact with this ionic molecule to make an ion dipole interaction. Remember, we chemists are not clever namers. Ion dipole interaction, ion dipole interaction. When this happens and you have enough water around this one ion, this cation here can actually come apart. These water attraction to these ionic dipole interactions can actually overpower the ionic attraction, and now it's going to pull the cation. The water is going to pull the cation off of this solid lattice structure, and water is then going to surround it. So instead of having it being surrounded by a bunch of anions, this cation is now surrounded by a bunch of water, and that water is going to have a bunch of negative charges all around the cation. Same can be said for the anion, but in reverse. So this ion is here is going to be experiencing a bunch of ion interactions, and then the positive end of water molecules are going to start interacting with it. Again, ionic dipole interactions, and eventually those interactions are going to overpower the ionic interactions, and the anion will be surrounded by the positive end of water molecules. And that's how water can dissolve most things. Water is very polar. Those charges are very strong on either end, so it can actually go in and start interacting with a whole bunch of other material. So anything that has a charge to it, so polar molecules and ionic molecules, are going to be soluble in water for the most part. There's exceptions. We'll talk about that later on. So there's one other thing that we're going to need to talk about, and that's London dispersion forces. So even if you have something that isn't polar, that has no electronegative atoms, like in this case we have ethane here. Ethane, 2 carbon with hydrogens on, with 3 hydrogens on each carbon. There are still going to be some attractions. So remember, electrons move. Electrons move at random. Sometimes they're going to be on this side of the hydrogen. They're going to be over here. Sometimes over here, the electrons may be on this side of the hydrogen. And then in an instant later, they flip-flop, where the electron moves over here and this electron moves over here. So these electrons are going to be moving all over the place. Now remember that electrons are going to repel other electrons. There's going to have that electron-electron repulsion. So if these two atoms start getting close to one another, and it just so happens that all the electrons are going to be on one side of the atom, then that side is going to have a very slight negative charge, which will repel all the electrons to one side of your second atom, which means that we now have a charge. We now have a positive and a negative charge. And this positive charge is going to be attracted to the original negative charge. And this comes about just because electrons are randomly moving around. Eventually, they're going to start to attract to one another. Now, these are very, very, very weak interactions. This interaction is very, very weak, but you can actually build up. These guys do stack. So the more atoms you have in your molecule, the more atoms that you can get close to one another in your molecule, two different molecules, can lead to some pretty strong forces. So let's kind of look at that. So this chart kind of shows what I'm talking about. Here are a whole bunch of different carbons. This first one is methane. So methane is just a carbon with a bunch of hydrogens all around it. So a single carbon, and its boiling point is very, very low. In other words, it's going to be a gas for a long time. We're gonna have to get this to get methane down to negative 146 Celsius before it becomes a liquid. So that means that there's not a whole lot of intermolecular forces going on to slow that thing down, to keep that thing from having translational motion. Now, if we move to ethane, ethane has two carbons. Now, the boiling point's a little bit higher. We don't have to cool it down nearly as much because now we have two carbons, which means more hydrogens all around. Remember, there's a bunch of hydrogens all over the place. More hydrogens, which means more chances for those London dispersion forces to take effect. More atoms to bump up to another ethane. More of the molecule's a little bit longer. So whenever it bumps up with another ethane, more of those atoms can get next to each other, and more London dispersion forces can take effect. And if we go to propane, we add another carbon to this. Even longer, even higher boiling point. More London dispersions, higher boiling point. So butane is just around freezing. If we get butane too cold, where water starts to freeze, butane will actually start becoming a liquid. And that's because it's just one more carbon, more hydrogens, more London dispersion happening. If we include another one for pentane, now pentane is where we finally start seeing pentane becoming a liquid and not a gas above 0 degrees. Hexane, we do another one. This is where you start seeing hexane being a liquid at room temperature. All right, and I think that's going to be it for today. Hope you guys are having a good one. I'll see you guys later.